The final section for simple harmonic motion waves for this topic 4 is wave properties, and really it's probably better to be titled wave behaviors, because we're going to look at some ways that waves interact with their surroundings and with each other. And so first, let's start by just mentioning and reminding you that when we talk about waves, when we talk about things like wavelength and frequency, and then all the things we're going to talk about in this particular video, these apply to all types of waves. It doesn't matter if we're talking about sound waves, electromagnetic waves, water waves, earthquake waves, things like it doesn't matter. Any type of wave, these apply. And so let's start with I guess the most straightforward, the easiest one, and that's reflection. And reflection is simply a wave bouncing off a barrier. And anytime a wave traveling through a medium encounters some type of barrier or some type of transition into another medium, there's going to be reflection. You see it when a wave bounces off of a pier, water wave bounces off of a pier, or when you look in a mirror, that's because of reflection. The light or the sound or whatever it happens to be is hitting the surface and reflecting off, bouncing off. And we have two types of reflection, two basic types of reflection that we can use and then carry those models into our more complex waves. And the first is what we call fixed end reflection. And fixed end reflection is when, and we're going to use a wave on a string as our example. The wave is traveling down a string that is attached to something at the other end. You can see from this little animation that the wave travels down as a crest. When it gets to the fixed end, when it's reflected, it comes back, it's reflected off out of phase by pi or by 180 degrees. So it goes down as a crest, it comes back as a trough. And this essentially really has to do with the forces involved and the force that fixed end is exerting on the string is causing it to be flipped. Now if we have free end reflection, this is when you have that same wave traveling on a rope, but the far end is not attached to anything. It's not fixed to a post or tied to anything. And so here this little animation shows you what happens there, and you can see that in a in a free end reflection, the reflected wave is in phase with the initial phase, or what we call the incident wave. And so the pulse goes down as a crest, it gets reflected off of the free end, and it comes back down as a crest. So it's in phase with the wave going down. And these two particular types of reflection are important because they are good models for what happened in real life with a lot of our other waves that encounter new mediums. When a light wave hits a mirror and gets reflected off, it models fixed end reflection, and so it gets reflected off 180 degrees. When you have a wave traveling from one medium to another, if it's going from a more dense medium to a less dense medium, there's going to be partial reflection, and that partial reflection is modeled by this free end reflection idea. When it's going from a less dense to a more dense medium, it models the fixed end reflection. And so we see these ideas occurring a lot around us. The other aspect of reflection are the angles involved. And the actual law of reflection says that the angle of incidence is equal to the angle of reflection. So these angles, you can see them here on the screen. The incident wave is the wave that's coming in, and we'll talk about incident rays or incident waves when we're talking about reflection and refraction, but it's really just a fancy word for the incoming wave. And that wave makes an angle with what we call the normal line. And if you remember when we talked about forces, we had a normal force, and that normal force was perpendicular to the surface. Anytime we're talking about something that's normal to the plane, that implies, or that means, that it's at a 90-degree angle, or it's perpendicular to the surface. And so our normal line when we're talking about reflection is a line that's perpendicular to the surface at the point of reflection. And so then the angle between that normal line and the incident ray is our angle of incidence, and you'll sometimes see it symbolized theta I. Theta is our angle, I is for incidence, and then when it hits and bounces off, you have what we call the reflected ray, and the reflected ray makes an angle that we call the angle of reflection with the normal line. And again, we use the normal line just because it's a more accurate representation, and it's easier, especially when you have a non-planar surface, so you have a surface that's not just flat. Okay. So just a couple of diagrams here. The one on the left just shows multiple incident rays at the same time, and this is what happens when you have something reflecting off a mirror. You have a whole bunch of light rays all reflecting off of the surface simultaneously, and that's where you get your image from. And then the one on the right is more just to kind of give you an idea of why we use the normal line. You can see that there's a curved surface here, and so it's easier to draw that line perpendicular to the surface and use these angles here instead of the angles down at the bottom. Okay, then we have refraction, and refraction is when a wave actually goes into a new medium. And so we travel from one medium to another, and as that wave travels into the new medium, it's going to change speeds. If you'll remember from the previous set of notes, we said that the single thing that affects the speed of a wave is the medium through which it's traveling. And so if a wave travels into a new medium, it's going to change its speed, it's going to change its velocity. Now when this change in velocity occurs, it's also actually going to change the direction. It's going to cause the wave to change directions as it enters the new medium. When it encounters this boundary, though, in reality, and depending on what the type of boundary is, but if it's one where there's going to be some transmission of the wave, or where it's going to pass through, very rarely is there complete transmission of the wave. More often than not, you get partial reflection and partial refraction. So some of the light goes through and some of it gets reflected off. And you can see this a lot in windows. If you look in a window and it's brighter inside than it is outside, what you see is you get kind of a mixed image. You'll see a reflection of yourself in the window, but then you can also see what's outside of the window. And that's kind of this idea that some of the light's going to come through, but some of the light's going to be reflected, and you're going to see that effect. Now, when we have refraction, and we're looking at the angles involved in refraction, again, all of these lines are measured from the normal line, which is this line perpendicular to the surface at the point at which the wave enters the new medium, at the point at which the two mediums are in contact and the wave hits. So we have our theta 1, which is this top angle here, and again, this is the angle of incidence, just like before, the angle of incidence, which makes this ray right here the incident ray. And then once it changes, or once it enters the new medium, you can see how it's changed directions. This theta 2, this is the angle of refraction, not to be confused with reflection. It's the angle of refraction, and this is the refracted ray here. Let's make a better R there so you can tell what it is. And so it changes speeds as it enters the new medium. So in this case, in all cases, theta 1 and theta 2 are going to be two different values depending on something we call the index of refraction, which we'll talk about in a little bit. The image on the right just shows this same idea using planes instead of rays. Okay, and so here's our waves that are entering the new medium, and as they enter the new medium, they're traveling in a slightly different direction. But again, you can see here's your theta 1, here's your theta 1, those angles are the same. These are your angles of refraction, and they're going to be the same as each other too. Any light wave or any wave coming in at that theta 1 is going to be refracted by the same amount. And again, that amount of refraction is due or is dependent upon the change in the speed, the change in the velocity of the wave. And actually, if we, getting into the whys and things like that, it has a lot to do with the interactions of the light rays with the molecules at a quantum level. But one of the, I guess, kind of best ways that I found to describe it is, imagine if you're traveling down the road, you're traveling down the highway, and you have, let's see, how can we get brown on here? Let's say you have a whole bunch of mud over here on the side of the road. You're driving in your car, and you veer off to the side. These little things on the sides are your wheels. Okay, and so let's say you're driving off the road and you encounter the mud. Ooh, that's not quite what I wanted. Actually, but let's move this over here a little bit. Let's move this over here. Okay, so you're driving at some angle. You're starting out on the asphalt, and you drive off the road and you hit the mud. Once your tires hit the mud, they start to spin. And so if your tires are spinning, that wheel's not gonna push you forward as fast. So as we move forward, this front tire here is going to hit the mud first. And so if you can imagine that initial impact, here's that first tire, here's that tire, here's this tire, here's this tire. This tire right here is going to start spinning first. And so that right side of your car is going to slow down. But this tire over here, the tire that's still on the asphalt, that tire is going to continue to have the same velocity that it did before, and it's going to pull the car around. And so what's going to happen is when you enter the mud, you're going to be traveling at a different angle, because that tire that's on the asphalt last is going to pull the car around to a different angle before it enters the mud. It's kind of it's not a great analogy, but it'll hopefully help you kind of visualize what's going on there a little bit easier. It's the same kind of idea when we're talking about those waves entering new mediums. And then the opposite actually is also true. If you're coming from the mud where you're traveling slower and you hit the asphalt, that first tire that's going to hit the asphalt is going to speed up, or is going to travel faster, and it's going to cause the car to veer at a different angle. And so what you can see here, if you're going from a medium in which you're traveling faster, if you slow down in the new medium, the angle of refraction is going to be smaller than the angle of incidence. And so if you're slowing down in the new medium, the angle gets bent, or the light gets bent, or the sound, or the whatever the wave is, gets bent towards the normal line. If you're speeding up in the new medium, it gets bent away from the normal line. So if you travel slower in the new medium, the angle of refraction is smaller than the angle of incidence. If you speed up in the new medium, the angle of incidence is larger than the angle of refraction. So slowing down, the angle of incidence is greater than the angle of refraction. Speeding up, and this is when we go into the new medium, the angle of incidence is smaller than the angle of refraction. Okay. Now mathematically, this is related by what we call Snell's law, and this actually relates the incident angle and the refracted angle by the equation sine theta 1 over c1 equals sine theta 2 over c2. In this equation, our c's are the speeds in those two given mediums. So c1 is the speed in medium 1, c2 is the speed in medium 2, and then of course theta 1 is the angle in medium 1, theta 2 is the angle in medium 2. And so if we rearrange this, we get this ratio, the ratio of the sines of the two angles is equal to the ratio of the velocities. v1 over v2 is equal to sine theta 1 over sine theta 2. That ratio here of the change in speeds is what we call the index of refraction. We're going to talk about that in a minute. But if we're talking about really any wave, but let's talk about it specifically for light. If we look at it in terms of the index of refraction, this c over cm. C is the faster of the two speeds, or c is the speed of, in this case we're going to talk about it as the speed of light in a vacuum. C subscript m is the speed of light in some new medium. And so the speed of light divided by the speed of light in some new medium gives us that index of refraction, which is the same, it's just this ratio we're talking about here, v1 over v2, and it gives us this factor called the index of refraction. And every material has its own specific index of refraction, and it doesn't matter, again, if we're talking about light waves, sound waves, whatever. There's an index of refraction for air, for both sound and for light. Most of our examples are going to have to do with light. They're going to use light as the example, but realize that it works for all waves. Now, if we factor Snell's law, or if we factor this idea of index of refraction into our equation, into our Snell's law equation, we can turn it into n1 sine theta 1 equals n2 sine theta 2. And again, the n is the index of refraction, and so n1 is the index of refraction of medium 1, and 2 is the index of refraction in medium 2. And so now we can relate the two based on that. And again, though, realize that the n is simply that ratio of the speeds in the two mediums. In air, the speed of light is roughly the same as it is in a vacuum. It does change by a very, very tiny amount, but for our purposes, we can call the index of refraction in air 1. And so what that means is that the speed of light in a vacuum and the speed of light in air are the same.